in the previous lecture, we learned about resistors, capacitors, and inductors, how they function. In this tutorial, we are going to learn about resistance, reactance, and impedance, the opposition that is being offered by each of those individual components in a given circuit. So what is impedance? Impedance is a concept which is actually related to the AC circuits, okay, whereas the resistance is a concept which is related to DC circuits. Mostly resistance is associated with when you are doing a DC circuit analysis. Their calculation of the value is same, which is R equals to V over I. Again, that's part of the Ohm's law. So if you look at this graphics right here, we have a series circuit where you have this is going to be R because it's a resistance. Say you have some current that's flowing in the circuit. The resistance of this circuit is given by this equation, R equals to V over I, and then of course, you know, V is equals to I times R over here. In a DC circuit, if you are just simply going to look at the relationship between voltage and current, say you have voltage over here, and then you have current on the y-axis, keeping the resistance constant, you're probably going to look a straight linear line. As the voltage increases, the current is also going to increase. So that's a pretty simple relationship between V and I, as they are directly proportional to each other. In case of a circuit where you have inductor, remember this is going to be L because the symbol for the inductor is L. Again, you know, it's a series circuit. Say it has a current I. The opposition to the change in the current which is offered by the inductor in a circuit is referred to as reactance, and the symbol that we use is X for reactance. And because this reactance or opposition is offered by the inductor, there is going to be L in the subscript, and this is equals to because it's a vector quantity, so it's j omega L, where omega is the angular frequency, which equals to 2 pi f, and then L is the inductance of the inductor. So similarly, if I am going to look at the relationship between frequency and the reactance, notice over here, if the frequency increases, if this term in the equation increases, the reactance is going to increase, correct? Because they are directly proportional to each other. So the relationship will be something like this. So you'll see a curve like this. As the frequency increases, the inductive reactance is going to change. And also, by the way, since this reactance is offered by inductor, it's referred to as inductive reactance. Let's now look at the capacitive reactance. Again, it's the opposition to the change in the voltage. So there is some kind of opposition that is being offered initially in a circuit where you have a capacitor. So this is a positive terminal, this is a negative terminal of the capacitor. This is referred to as, again, reactance, and because it's offered through capacitor, so there's a C, and it's known as the capacitive reactance, and this actually equals to 1 over 2 pi FC, okay? So again, if you try to look at the relationship between the capacitive reactance and the frequency, as the frequency increases, because it's in the denominator over here, the numeric value of the denominator is going to increase. That means this value is going to be extremely small. So as the frequency increases, capacitive reactance is going to decrease, and there's an inverse relationship between them. So it's going to look something like this. Okay, so that's the basic difference between resistance, inductive reactance, and the capacitive reactance. Okay, let's now move on to understanding what impedance is. And a good way to understand impedance is to think of this circuit right here, where I have the resistor that has some resistance. Say this is R, and I'm just going to give some values to it also. Say this is 150 ohms. Inductance, inductive reactance, say that is 259 ohms. By the way, the inductive reactance and capacitive reactance, they both are also measured in ohms. And then the capacitive reactance is going to be say 193 ohms. Okay, so this is your XC, this is your XL, and obviously this is your R. It's a series circuit, and you have some signal with some kind of magnitude plus phi. Say this A is some magnitude right here. So okay, all right, now remember your total reactance in this circuit, and I'm going to say X here, is going to be the sum of the inductive reactance plus the capacitive reactance. Okay, and in order for us to find out the total impedance, which is going to be the sum of the resistance plus the reactance, we have to get this impedance using the Phasor diagram. And that's where it's very important to learn how Phasor diagram work, and we will use these diagrams to calculate the impedance. Okay, now the vector representation of resistance is usually drawn on the x-axis of the of this graph. Okay, so say this is the resistance. The capacitive reactance, the vector representation of the capacitive reactance is drawn on the negative y-axis. So say this is your XC, and then the vector representation of the inductive reactance is drawn on the positive y-axis. Okay, so I've tried to match these magnitudes for resistance, capacitance, and the inductance according to these values that I have over here. Okay, all right, now because I already mentioned that reactance is going to be the sum of the inductive reactance and the capacitive reactance, and because both values are given, so let's just add them. XL is how much? It's 259 ohms. 59 ohms. I'm gonna have a minus here, and the reason I have minus negative sign here is because if you look at the capacitive reactance, it's on the negative y-axis, right? Negative y-axis. So in this case, we will have a negative sign, and XC is how much? It's 193 ohms, and that gives you, if you do the math, it comes down to 66 ohms. Okay, now if I am going to draw this 66 ohm, which would represent the total reactance, it will be, because it's a positive value and a reactance is on the y-axis, it will be somewhere over here. So say this is my X, which is 66 ohms over here. Now the impedance is basically now the sum of these two components, which is the reactance and the resistance. I can, if I want, I can move this reactance around to over here, as long as the magnitude is same and the direction is same. Make sure that the tail is touching the head of the resistor, and then I can just simply apply Pythagoras Theorem to add these two components R and X to calculate the total impedance. Now what does Pythagoras Theorem suggest? So this represents, I'm going to change the color here. So this represents base here, this represents vertical parallel, and this represents hypotenuse, which is basically our impedance. So hypotenuse square equals to perpendicular square plus base square, correct? That's what the Pythagoras Theorem is. If I take a square root, then this would be h equals to under root parallel square plus b square. In this equation, I'm now going to replace the values, these expressions, h with z, because h represents the impedance over here, equals to under root, p represents the reactance, total reactance, x square, plus base represents the resistance, so r square. In some books or somewhere you will see z equals to under root xl minus xc whole square plus r2, And that is also fine, because remember XL minus XC comes from here. Okay, remember XC represents the negative y-axis, so this is going to be negative then, XL minus XC. So both are pretty much same. I'm going to plug in the values given in the circuit and find out the impedance of the circuit. I have already calculated this part right here, which is what, 66 ohms. So taking a square of that, plus resistance is 150 ohms, square of that. If I do the math, it will, let's see, if we do the math here, what do we get? We get somewhere around so we get 164 ohms. Okay, now there's one more thing to it. Okay, so that's the total impedance which is offered by this circuit over here. Z equals to 164 ohms. Okay, the one thing that's interesting, because the impedance because the reactance was on the positive y-axis, so this circuit has a more inductive nature than the capacitive nature, because the reactance was in the positive y-axis. Okay, so that means current is going to lag voltage, and if you are interested like from like at which angle it is going to lag, or in other words, if you're wanting to try to find out this angle, which is phi, the equation for that is tangent arc, and then phi equals to x over r. So your phi is going to be, if you plug in the values for x, which was 66 ohm, r was 150 ohms, you should get 24 degrees, and that's what the angle is. Okay, so the current lags voltage by 24 degrees. So that's what resistance, reactance, and impedance are. Remember, impedance is the total opposition that comes from the reactance and resistance in a given circuit. Also, if I go back to the previous slide here, and I use the value, same value from the same example, 159 ohm for resistance, inductive reactance was how much? 259 ohms, and then 193 ohms for the XC, XL, and then resistance over here. I can find out the current using this equation over here, I equals to V over R. So say V is 200 something, okay, in all three cases 200 volts. Okay, so you plug in the numbers and you should be able to find out the current. And similarly here, I equals to V over XL. So V is 200, XL is going to be 259, and then similarly over here, I equals to V over XC, where V is the 200, and then XC is 193 ohm. And remember, how do you find out XC and XL? You have this equation. If you have the frequency known, and then if you know the value of the inductor and capacitor, you can plug in the values over here in this equation and in this equation and find out the total reactance. So I hope you enjoyed this lecture, and I shall see you in the next videos. Thank you for watching. Bye.